All right, we're in our final section of the chapter. This is section 6.9, and we're going to be covering a very important theorem known as the rational zero theorem. Okay, this is a theorem that you're going to use to find zeros of a function when all of the other methods and approaches that we've learned so far in this chapter have failed us. Okay, so here's what the rational zero theorem states. It applies to a polynomial function, so you have to be working with the function in its standard or expanded form. Okay, it's got to be in this format. And the theorem states that the possible rational zeros of the function will be p over q, where p is a factor of a sub 0, which is your constant, and q is a factor of a sub n, which is your leading coefficient. Okay, so a couple things here. First of all, understand this theorem only gives you a list of possible rational zeros of the function. It's not going to tell you directly the actual rational zeros. You're just going to have to test them out to see which one works, okay? And I think other key word here is rational, all right? This theorem only will lead you to rational zeros directly, but the good thing is if you know some of the rational zeros, we've learned some other techniques that can lead us to the irrational and complex ones as well, okay? And notice what the theorem wants you to focus in on from the function itself. It wants you to focus on the constant and the leading coefficient of the function. You're going to find factors of both of those numbers, and then you'll use those factors to make a fraction or a list of fractions as the potential rational zeros for the function, okay? So as kind of a quick little example here, let's say that our function f of x is this 2x cubed plus 3x squared minus 8x plus 3. So this theorem's wanting you to focus in on the 3 as the constant and the 2 as the leading coefficient. 3 has factors of 3 and 1, and then 2 has factors of 2 and 1. So notice what letters I'm assigning to each of those. 3 and 1 is being assigned to the letters P, 2 and 1 is being assigned to the letters Q. And now what I do is I make a list of P over Q. I take each value of P and put it over each value of Q, considering both positive and negative values. And what that gives me is a list of potential rational zeros. So these values right here, plus or minus 3 halves, 3, 1 half, and 1, those are the only potential rational zeros of this function f of x. All other rational numbers can be excluded. Okay, so let's take this further now. All right, find the zeros of the function f of x. Okay, and notice it says to also give the factored form of the function. Okay, so first thing to notice is that the function f of x, I don't know any factoring techniques that are going to work for this. Okay, grouping isn't going to work here. It's not a sum or difference of cubes. It's not a quadratic pattern. And I'm not given any other information about the function other than its equation, okay? So that's kind of my indication that I need to use this rational zero theorem, okay? So first I will find factors of my constant, okay, which is 5 in this case. The only factors of 5 are 1 and 5, and you've got to consider them as both positive or negative, okay? Then I will find factors of my leading coefficient, which in this case is 6. I will assign those to the letter Q. Okay, factors of 6 are 1, 2, 3, and 6. Again, considering positive or negative for each. Okay, so now I take my P values and I place each of them over each of the Q values to make my list of possible zeros. Okay, so a p-value of plus or minus 1 over a q-value of plus or minus 1 is going to give you plus or minus 1. A p-value of 1 over 2 is going to give you 1 half. A p-value of 1 over 3 is going to give you 1/3. And again, notice I'm putting plus or minus on each of these. A p-value of 1 over 6 is going to give you plus or minus 1/6. I've exhausted all the combinations with the p-value of 1, so now I move to the p-value of 5. Okay, I take 5 and place that over each of the q values. That's going to lead me to plus or minus 5, plus or minus 5/2, plus or minus 5/3, and plus or minus 5/6. Okay. So notice the list that's in blue here. There's, if technically you consider the plus and minus, you have a total of 2, 4, 6, 8, 10, 12, 14. There's 16 numbers there. Okay, 16 possible rational zeros for the function. Clearly not all 16 of them are going to work based on the degree of this function being 3. At most, only 3 can work. Okay, so how do I know which ones that work? Well, I got to test them, and I'm going to test them based off of my remainder theorem and that process of synthetic substitution. I'm using the remainder and factor theorems with synthetic substitution, okay? Now, since I'm going to be testing multiple numbers here, I'm going to give you kind of an abbreviated way of doing your synthetic substitution, okay? So we're going to make kind of a little chart here. I'm going to put the coefficients of my function up top. So 6, -7, -8, and 5. And then the numbers that I'm trying to test, technically the numbers that I would put in the box for synthetic division, I'm going to put over on the left-hand side here. Okay, so let's test the 0 of 1 first. Okay, positive 1. That's the first number in the list right here. So I'll put a 1 there. Again, that's like the number that's going in the box. And I'll bring the first coefficient of 6 down. I take that number 6, I multiply it by the 1 from the box. Normally we would write that down, but now we're just going to kind of hold it in our head. So 6 times 1 is 6. Add that with the next coefficient of -7, and you get a -1. Now the process starts over. Take -1 times 1, which is -1, add it with -8, get -9. -9 times 1 is -9. Add that with 5, you end up with a -4. And we know that last number is supposed to be our remainder, right? Well, I need the remainder to be 0 for 1 to be a 0 of the function. I don't have that here, so I can rule 1 out. Okay? So I move to the next number in my list. Right? If you're looking at the blue list of numbers there, I would say my next number would be -1. Okay? Bring the 6 down. 6 times -1 is -6. Add that with -7, you end up with -13. Okay? Take -13 times -1, add that with -8, you get +5. 5 times -1 is -5, add that with 5, you get 0. And that's what I was looking for. I want a remainder of 0. That tells me that -1 is a factor, or I'm sorry, is a 0 of my function. Okay, so this leads me to a slightly factored form of the function. If -1 is a 0, then x plus 1 is a linear factor, and then these three numbers will lead me to a quadratic factor of 6x squared minus 13x plus 5. And now the focus is on this guy, the quadratic factor. See if it factors further, which in this case it does. It factors to 3x minus 5, 2x minus 1. All right. So this is my fully factored form of the function f of x, and then my remaining zeros come off of those last two factors. So altogether, I'm going to say that this function has zeros of x equals -1, of 5/3, and of 1/2. Okay? And I want you to notice that all three of those numbers are rational numbers, and notice that they show up in my list of possible zeros, p over q, right? We had of course the -1 there. we have the 5/3 here, and we have the 1/2 here. So it's just validation that these should be zeros of the function. All right, one more example. This one's going to be a little bit more involved. Okay, so find all the zeros of f of x. This is a pretty large function with a degree of 4. I don't know any other factoring technique that would work for this function, grouping, quadratic pattern, or anything like that. So I really have no choice but to use the rational zero theorem with the p's and the q's, okay? So let's start with my p's. They come off the constant. There's a lot of them in this case. P could be plus or minus 1, 2, 4, 5, 10, or 20. And then Q comes off the leading coefficient. Now the nice thing in this case is the leading coefficient is 1. Okay, and the only factors of 1, of course, are 1 and -1. Okay, so if I take each of the P's and put it over each of the Q's, it's not going to be too exciting here. My list of P over Q's is really just the list of P's. Plus or minus 1, 2, 4, 5, 10, and 20. Okay, so now I start to test. All right, we'll make that chart. My coefficients from my function are 1, -4, 1, 16, and -20. And the first number in my list of P over Q's to test would be +1. Okay, bring this one down. 1 times 1 is 1. 1 plus -4 is -3. -3 times 1 is -3. Add it with 1, get -2. -2 times 1 is -2. Add that with 16, get 14. 14 times 1 is 14. Add that with -20, you get -6. So the remainder is not 0. Conclusion, 1 is not a 0 of this function. Okay. Next, I'll try -1. Bring the 1 down, the first coefficient. Take 1 and multiply it by the -1. You get -1. Add that with -4, your next coefficient. You get -5. Take -5, multiply it by -1. You get 5. 5 plus the next coefficient of 1 gives you 6. 6 times -1 is -6. Add it with 16, you get 10. 10 times -1 is -10. Add it with -20, you get -30. Still don't have a remainder of 0, so cancel out the -1, and in your list here you can just cross both of those off. Okay, so now move to the next number in your list. Let's try +2. Bring the 1 down. 1 times 2 is 2. Add it with -4, you get -2. -2 times 2 is -4. Add it with 1, you end up with -3. -3 times 2 is -6. Add it with 16, you get 10. 10 times 2 is 20. Add it with -20, you get 0. Nice. That's what I was looking for. There's my first 0 of the function. Okay. So I'm going to say that f of x has a slightly factored form of x minus 2, right? If 2 is a 0, x minus 2 is a factor. And then I use these 4 numbers to lead me to another factor. Now notice the original function, it has a degree of 4. So after I do one synthetic division, the resulting quotient will have a degree of 3. So this corresponds to 1x cubed minus 2x squared minus 3x plus 10. Okay. And now the focus should be on this cubic. All right, I want to try and find the zeros of that. All right, and here's what's difficult about this. I don't know how to factor that cubic. In the last example, when we got to this spot, we were able to factor because it was a quadratic. Not the case here. Okay, so what's that mean? I got to do P's and Q's again. Okay, I now need to use P's and Q's, the rational zero theorem, on x cubed minus 2x squared minus 3x plus 10. Now here's the good thing. Your list of P over Q's from above, you can use the same list and you can actually rule out some numbers, okay? Your coefficient and your constant here are 1 and 10, okay? Well, that allows me to rule out plus or minus 20 because 20 is not a factor of the constant of 10. And it also allows me to factor or rule out values of 4 because 4 is not a factor of 10 as well. Okay. So we need to do this testing process one more time. I'll copy the coefficients of 1, -2, -3, and 10. And then I start testing numbers from the same list of P over Q's from above. I don't have to test 1 and -1 again, because if they didn't work for the larger function, they're not going to work for the smaller factor, okay? I should test 2 a second time, though, because there is a possibility that 2 could repeat. So let's try that one more time. Bring the 1 down. 1 times 2 is 2. 2 plus -2 is 0. 0 times 2 added with -3. -3 times 2 added with 10. All right, it doesn't work a second time. So rule 2 out as a second value. Move to the next number in the list. How about -2? Bring the 1 down. 1 times -2 is -2. Add that with -2, you get -4. -4 times -2 is 8. Add that with -3, you get 5. 5 times -2 is -10. Add that with 10, you get 0. Nice. So -2 is also a 0 of the function. And now I can give you a slightly more factored form for the function. I can say that f of x equals our original factor of x minus 2 times x plus 2, and then use the 1, the -4, and the 5 to give me a quadratic factor, x squared minus 4x plus 5. Okay. All right, now I'm not done. I found 2 zeros for the function, but it should have a total of 4. The degree of this function is 4. The other 2 zeros are going to come off of x squared minus 4x plus 5. Okay. Now, unfortunately, that one is not factorable, but here's the nice thing. It's a quadratic expression or quadratic factor, so I don't need P's and Q's on that anymore. Why? Because I've got completing the square and I've got the quadratic formula that can be used to solve a quadratic equation when factoring doesn't work. Okay, so now we're here trying to solve this equation. Let's do, again, you could do completing the square or quadratic formula. I think completing the square will be quicker. All right, move the 5 to the other side. Half of -4 is -2. Square it, you get 4. Then we factor. Square root x minus 2 is equal to plus or minus I. Add 2 over, you'll get 2 plus or minus I. All right, so there's your final 2 zeros. They are complex zeros, okay? And that just tells me that had I tried P's and Q's on the quadratic, I wouldn't have got any of my my list of P over Q's to work because they would only have been rational numbers and the final zeros here are complex numbers, okay? So in the end, we're saying that this function has zeros of 2, -2, and then 2 plus or minus I for a total of 4 zeros. Okay. All right, it is your turn. Try practice one yourself. It's not quite as involved as this example. It's a little bit more like example 1. So try that yourself. Pause the video as you do so. Check your work with mine.